Hello, Algebra 2. In this video lesson, I'm going to talk you through Chapter 7.4 of your textbook, Inverse Functions. Let's start by talking about a broader category, inverse relations. You'll probably remember from the beginning of the year we talked about the idea that you could put together or map any pair of sets of data, let's call them x and y, and that would be a relation. And so we talked about all sorts of different examples, such as shoe size and height, but also shoe size and hair color. And some of them make sense as functional relationships, and others don't and are simply called relations. If you want to talk about the inverse relation of a particular relation, all you're doing is swapping the x and the y. So notice the red set here on the right is simply the reverse, or really the inverse, of the blue set on the left. If you have a particular equation like this one, and you want to find its inverse, again, all you do is swap the x and the y. Now, most of us don't know how to make use of an x equals equation nearly as well as a y equals equation. So traditionally, we rewrite it to become a y equals equation, which means we move everything else over and isolate y. And so that's what we've done here, and y becomes 1/2 x plus 2. And this equation, this relation, is the inverse of the original. If it comes to graphing an inverse relation, in that case, the original information, like this on the left, is reflected through a mirror line, and that mirror line is this 45-degree line called y equals x. So notice that every blue point in the original, let's take this one and find it over here, is mirrored all the way across to the other side of the 45-degree line here. So ones that are closer to the 45-degree line, like this one, are closer, and ones that are on the 45-degree line, like this one, remain on the 45-degree line, called y equals x. And those that originally were on the, well, let's call it the bottom right side, I guess, of that 45-degree line, they actually end up on the top left side of that 45-degree line. So every one of these is mirrored over, and this graph here is the graph of that inverse. So let's talk about some that are graphs of equations. Of course, we know how to graph y equals negative 3x plus 5. You plot the intercept and work the slope, draw a line through it. That's the graph of y equals negative 3x plus 5. If I want to graph the inverse of that, I've got to mirror it. In other words, I've got to mirror every point across that 45-degree line. Well, it's pretty easy when it's a linear equation. We've said before that a linear equation, you only need 2 points to graph it. So I'll just mirror the 2 points that I had. The red ones are mirrored as the blue ones. I draw a line through that. Now I can get rid of the mirror and the original. This is the graph of the inverse relationship here. Notice this time I've chosen to just leave it as x equals. That's fine. Now, for number 6, if I want to graph the inverse of that, well, if you've forgotten how to graph an absolute value equation, and I hope you haven't, it has been a couple of months though, but if you have, remember, you can always simply substitute values in. We're essentially saying y is equal to the absolute value of x. So what would happen if you put in 0? Well, y would become 0. But if you put in 1 for x, you'd get negative 1. Then again, if you put in negative 1 for x, you would also get 1 for y. If you put in 5, you'd get 5, but if you put in negative 5 for x, you'd also get 5. So I hope you remember now that the shape of absolute value graphs is a V shape, like that. Okay, if I wanted to do the inverse of that, well, the right side of that is directly, in this particular case, on top of the mirror line. So it's really going to be this piece that's going to be mirrored. These 3 red dots are going to remain on the mirror line. So there they are as blue dots. It's these other 2 dots that I've drawn here that get mirrored over here. So I change my graph, get rid of my mirror line, my red dots. This is the graph then of the inverse. X equals the absolute value of y. So I'm not going to ask you to graph any right now. Instead, I'd just like you to think about these. The top row, the ones with numbers, have inverses that match with them on the bottom row, the ones with letters. So hit the pause button and figure out what those matches are, and when you come back, I'll show you the answers. Okay, I'm going to assume that you've paused and are back now to see the answers. These were a little harder than the ones that I showed you in the previous slide because now we're talking about um, uh, uh, relations that change their path rather than keep a fairly constant path. Even with absolute value, it was still pretty much a straight line trajectory for most of the way, just one bend along the way. So let's uncover these and see what those matches are. And so I hope that you were able to apply visually, even if you didn't actually draw these out, those 45-degree lines, and then you were able to mirror every point. So here's the 45-degree line for that one. Mirror every point in the top row and figure out what the mirrored result would be in the bottom row. Now, to determine whether or not these are functions, we've been talking about relations up until now. Well, remember the vertical line test that we've talked about before. And these are those results. This one on the left is the inverse, and it's actually the graph of x equals negative 3y plus 5. And the one on the right is the graph of this inverse here for number 6. Vertical line test is passed for the one on the left. It's not for the one on the right. So while the original, which is under the, here I'll uncover it there, f of x equals the absolute value of x, although that is a function, its inverse, x is equal to the absolute value of y, is not a function. Doesn't pass the vertical line test. There's an easier way, though, called the horizontal line test. You didn't really have to go through all of the work to regraph the inverse. You could have instead applied a horizontal line test to the original. So here are those originals, and if the horizontal line test is violated because you hit 2 points in any horizontal slice, like I would here, then the inverse of this is not going to be a function. If I draw horizontal lines through this, I can keep doing that forever, and I'll always only hit 1 point. So the inverse of this is going to be a function just like the original is. Okay, so based on that, hit the pause button again and figure out for yourself for number 4 and number 7, will the inverses of these be functions or not? Okay, I'm going to show you the answers now. For, oh, I've got these backwards. No, I do have them in the right order. For number 4, notice this is a quadratic, and so of course it's going to be a parabola shape. And if you didn't remember how to graph quadratics, and I certainly hope you do, final exam's not that far away, you could have always plugged in values. So if you plugged in 0 for x, then you would have 0 minus 3 or negative 3, like I had here. If you plugged in 1 for x, then you'd have 2 minus 3 or negative 1, like I have here, and so on. And so I've graphed this parabola. But you can see that if I did a horizontal line test, it wouldn't pass. So while this is a function, its inverse, which is going to turn sideways, is not going to be a function. On the other hand, this one, the graph of 3 minus 2x, I can do horizontal lines as often as I want. I'm never going to hit more than 1 point. So the inverse of this will be a function just as the original is. All right, now moving on to example 2 out of the textbook. How do you verify that the inverse is a function? I'm sorry, how do you verify that two functions are inverses? Well, first of all, the test that's easiest to do to see if two functions are inverses of each other is to do compositions of each other. If you put f on the outside and g of x on the inside, you should turn out with x. Likewise, if you put g on the outside and put the f function on the inside, again, you should turn out with x. If that's true, if both compositions turn out to be x, then you have inverses of each other. Notice some notation that the textbook has started to use. F to the minus 1, and this is really the only place that it explains it as far as I can remember in the book. F to the minus 1 is read as f inverse. So instead of calling it g for the second function, they might be calling it f minus 1, and that's telling you that it's the inverse of the other one. So they're saying verify that these are inverses. They're saying it, they're indicating that it is. they're saying that this is going to be the inverse of that by calling it f minus 1 rather than g. But to verify it, what you're going to do is you're going to do compositions of the two. So to remember to do the composition on the one on the left, change that x to parens and put the other inverse in it. Likewise, to find the inverse of that, replace that x with parens and put the other one in that one. So that's what they've done here. They've moved this into those parens, like I said, and likewise over here, with the parens I've indicated, they've moved this function, 2x minus 4, into the parens. Now you simply work it out to see if you end up with x, simplifying away, and you find out that you do on left and right. And you verified that those two originals that you had were inverses of each other. Based on that, work with the example I've given you here, and when you come back, I'll tell you whether or not those are inverses. Okay, I'm going to assume that you've done that. They are inverses. I'm not going to walk through every step. I'm just going to show you that on the left, replacing the x with parens, putting the other function inside it. Well, if I've got a cube root inside parens and I'm cubing it, those cancel each other out. I would just end up with 2x. A half of 2x is x. On the right side, I've done the reverse order. I've got g on the outside, but it also is going to simplify down to x. So those two, f and g, are inverses of each other. Now, if you have to find inverses when functions aren't linear, if you got to find that inverse as opposed to verify that it's an inverse. Let's say that you're given x squared. Notice that they make the caveat here, the domain restriction here, x has to be more than 0 for this to work. And here's why. The blue graph is the graph of x squared. Remember, it's going to be a parabola because it's a quadratic. And like the example I showed you earlier, when you turn that sideways or mirror it across this line, this 45-degree line, it's not going to pass the vertical line test. But if I only talk, as I say here, if I only talk about x being greater than 0, then I'm covering up these quadrants, and I'm really only looking at this blue portion of the original, and its mirror is this red portion. And neither of these is going to violate the test for functions. Okay, so from this point then, it's simply a matter, like before, of swapping x and y, and simplifying down. And when you simplify down, you're going to find that y is equal to plus or minus the square root of x. But remember that you restricted the domain. So in this case, you're really only talking about positive square root of x. That's that red arc that you have there. And in that case, you found the inverse of the original blue. If you have an equation that's a cube as opposed to a square, you don't have these problems. So what you're going to find, and we've talked about this numerous times before, even powers, quadratics, fourth degrees, sixth degrees, eighth degrees, and so on, those are going to violate the horizontal line test. Odds, and this blue one here is the original odd, this S shape, they won't violate the horizontal line test. So their inverses will be functions just as they are. So if you want to find the inverse of this, well, you're going to begin by graphing. So the easiest way to begin by graphing is to do it with a graphing calculator. So I do recommend that you have that handy just to make sure always that whatever function you're starting with, you've checked to see whether or not its inverse is going to be a function as well. By doing the horizontal line test, this one passes. So then, like before, all you're going to do is switch x and y, and you're going to end up finding that when you take the cube root of both sides, that y, or in other words, f to the minus 1, is equal to this. That's the inverse. Last example. Hit the pause button. When you come back, I'll show you the answer to that inverse. Okay, I'm going to assume that you've paused, and here's the answer to the last question. There it is. Hit the pause button and study that if you need to. Don't hesitate to come in with questions. That's the end of this video lesson.